as I mentioned in the last example, this particular function does not have an inverse function, and you're going to see why as we go through the steps. So what we'll end up doing is restricting the domain. And I'll show you what that looks like too. So let's go ahead and proceed with our steps. The first step is that we replace f of x with y. So we have, for our first step, y equals x squared plus 2 and then for our second step, we interchange x and y. So we have x equals y squared plus 2. As you learned in a previous section, this is not a function. Notice here that we have an even power of y. And we're going to continue those so that you can see, again, why that's not a function. So step 3, I'm going to solve for y. So the first step of solving for y, I'm going to go ahead and write it as y squared plus 2 equals x, so that I have the y on the left side. And then I'm going to subtract 2. So these are going to cancel. And I have y squared equals x minus 2. The next part of the solution process is, since y is squared, we want to solve for y, not y squared. So to undo squaring, the inverse operation is square rooting. So we're going to take the square root of both sides. And so these two operations cancel. So when you take the square root, just remember that since we're taking the square root of a variable, we have to put plus minus. And so with this, we have plus minus the square root of x minus 2. You can see right here that we have y equal to two different expressions for x. If you need to see more clearly the two different expressions, we have y equals negative square root of x minus 2. And we have y equals positive square root of x minus 2. So this is not a function. We can only have y equals a single expression of x in order for it to be a function. Every x value can only go to a single y. And in fact, we should label this as y1 and y2 because you can see here that they are two different relations. And so you have this x value here corresponding to two different y values. So that is not a function. Now, because of this, we can't actually proceed to step 4 because step 4 says if the equation for y represents a function, then replace y with f inverse of x. So our condition here is not satisfied. It's not a function. So that means that we can't replace y with f inverse of x. And so we're not even going to proceed to step 5 either. Because the only reason we would go to step 5 is if we think they're inverses and we're trying to show that. But what we will do is go ahead and graph the inverse relation. And we can use the property that we can swap our inputs and outputs. So we're going to go ahead and make a table of our original points and swap them out for inverse points. Now keep in mind that this is not an inverse function that we're making a table for, but an inverse relation. So we're not going to be able to label it f inverse of x. We're just going to put y in our output column. But I do want you to see that even if it's not an inverse function, if we have an inverse relation for f of x, we still swap out the x and y values. That property still applies where we have reflectional symmetry over the line y equals x. So we're still going to swap x and y. Another thing that we could do, we're not going to do this, but we did discuss this in the last section, is we could use transformations to graph this if we wanted to graph it by hand. You could graph each, we separated the inverse relation into y1 and y2. We could graph each of these as a transformation of the square root of x. That's what the parent function is. Notice for here that we have -2. We have -2 here as well. So this means that we would go right to for our parent function square root of x. And then this negative up here means that we reflect over the x-axis. So I'm going to go ahead and write those down so that you can kind of see that as we're going along. That should be true. But again, I'm going to use instead to graph it the original table and the inverse table. Okay, so let's go ahead and pick some points from f of x and put them on our table. So we have x and we have f of x. So notice here that we have the point -2, 6. We have the point -1, 3. We have the point 0, 2. We have the point 1, 3. We have the point 2, 6. So we have the point -2, 6, -1, 3. All right, we have the point 0, 2. We have the point 1, 3. And we have the point 2, 6. So now let's go ahead and graph the inverse points. We're going to go ahead and put x as our inputs. And since this is an inverse relation, it's not an inverse function, we can't put f inverse of x for our output, but it's just going to be y. Okay. But it's the same procedure with the table. We're going to swap our x and y values. So -2, 6 switches to 6, -2. -1, 3 switches to 3, -1. 0, 2 switches to 2, 0. 1, 3 switches to 3, 1. And 2, 6 switches to 6, 2. And while I have my blue pen, I'm going to go ahead and write down the inverse equation here. So we have y equals plus minus square root of x minus 2. And so if you remember, one of the main ways to distinguish between functions and non-functions when you're looking at tables is that the x's should not repeat if it's a function. So notice here, 6 repeats. Also, 3 repeats. But really, these are just a few points that we picked out. If you think about it, you'll realize that we have an infinite number of repeating x values. But we just need to show that 2x's repeat for it to be disqualified as a function. So this is not a function. But let's go ahead and graph it just using these points so that you can see what that looks like. And this will also help us to transition to our discussion of one-to-one. And we'll determine how to look graphically at a function and see if it is one-to-one. So let's go ahead and plot our points. So we have the point 6, negative 2, 3, negative 1, 2, 0, 3, 1, and 6, 2. We're going to go ahead and connect those points. And so here's our graph. Now, if you remember, to test graphically whether a relation is a function, we use the vertical line test. So let's go ahead and try that on the inverse relation that we have here. And so here's our vertical line. Notice as I move the vertical line across the graph, you can even see like the points that we pointed out, like right here, the point 3, negative 1 and the point 3, 1. Those are the intersections with this vertical line here. You can see that clearly. But really, just like we said with the table, if that vertical line crosses anywhere on the graph more than once, it is not a function. So this fails the vertical line test. This is not a function. I'm going to write that down. All right, so I also went ahead and wrote down what we saw in the table. So x values repeat in the table, so the inverse relation is not a function. The inverse relation fails the vertical line test, so it is not a function. So those are the two things that we have discussed here. Now, what I want you to think about is, since the x and y's are switching here, well, that means that if the inverse relation is failing the vertical line test, then the function must be failing a different type of line test. Well, vertical has to do with the y values. So if we swap it out, then we're failing a test for the function that has to do with the x values. And that test is actually called the horizontal line test. So remember, the horizontal axis is the x-axis. So I'll illustrate that for you real quick. So here's my horizontal line. Notice that as I run it up and down the function f of x, that I'm crossing in 2 points really for an infinite amount of times, right? But you can see a couple of precise points here. This is the point negative 2, 6, and this is the point 2, 6. Those are some points that we see here in the table. But notice when we look at the table that we have repeated y values, right? So same thing here with these 3's. These are repeated. And if you notice, that's going to be another place on the graph where the horizontal line crosses more than once. So really there's only one place where it crosses once. And that's the same place where the vertical line crosses once, with the corresponding points. Like this is 0, 2. This is 2, 0 on the inverse relation. There's only going to be one where there's only one intersection of either your horizontal or your vertical line for the two relations that we have here. So I've just shown you that f of x fails the horizontal line test. If it fails the horizontal line test, and that means that its inverse is going to fail the vertical line test. So the inverse will not be a function. This is a key indicator of a function that is not one-to-one. A function that is not one-to-one is not invertible. In other words, every y value does not have a unique x value, like we have here with 6, right? The y value of 6 has two different x values. So I'm going to go ahead and write that down, and then I'm going to give you the precise definition of a one-to-one function. All right, so here's the new information that I've added. Y values repeat in the table of f of x, so it is not one-to-one. The graph of f of x fails the horizontal line test, so it is not one-to-one. Now, on the next slide, I'll just give you a precise definition of one-to-one, but I felt like it was easier for me to show you visually an example of something that is not one-to-one to understand what one-to-one means. This function here, f of x here, was one-to-one, right? Every x value goes to one y value, which makes it a function. And then every y value only has one x value going to it, which makes it one-to-one. But let me go ahead and write that down. Okay, so here's our definition of one-to-one. A function is one-to-one if every element of the range or output corresponds to exactly one element of the domain or input. So again, in this case, f of x is one-to-one. There are no y values that you see here that correspond to more than one x value. If you wanted to, you could perform the vertical line test on it, and you're going to notice it doesn't cross anywhere on our function f of x more than once. So it is one-to-one, which again means that it is invertible. Invertible meaning it has an inverse function. This function here is not one-to-one. It fails a horizontal line test, which means that it is not invertible. It does not have an inverse function. So here's that point written out. Functions that are not one-to-one are not invertible, meaning they don't have inverse functions. They may have inverse relations, but not inverse functions. Before I can finalize this, I just want to show you real quickly that even though these aren't inverse functions here, with them being inverse relations like this, they still have that reflectional symmetry over the line y equals x. So I'm going to go ahead and draw that. All right, so you can see that here. You can see that, kind of tilt your head to the right again. You can see that this line y equals x is kind of like a mirror reflecting the two images across of f of x and the inverse relation here. And lastly, just before we leave this, why not go ahead and review real quick just the transformation for the square root of x. So notice that the square root of x graph is here as a parent function. And we mentioned earlier that the two relations we got, y1 and y2, were just transformations. For y1, this negative means that we reflect the square root over the x-axis, and then we're also moving to the right 2. So if you reflect this over and you move it to the right 2, you get this bottom portion of the graph. And this is actually, this bottom portion is y1. So if we wanted to, we could just separate this into y1. This top portion is y2. That's what I have right here. And that's just a shift right of 2 of our square root of x. So you can see if we have that here, it's just moving over 2 to the right, and we have that, we have y2 right here. And I can go ahead and write that down for you. Now notice here that y2 is a function and y1 is a function. Just when you put them together, that's not a function. So I could have restricted my domain of f of x. I could have let it be from 0 to infinity, or I could have been negative infinity to 0. If I picked either section of that by restricting the domain, then the inverse for that would have been a function, because the inverse you can kind of see graphically here. If I go from 0 to infinity, that's this piece. That would go with this top half right here, which is the positive square root of x minus 2. But if I had restricted it down to the negative values up to 0, then I would have had the bottom half here, which is just the negative square root of x minus 2, y1. So by restricting the domain of f of x, I could have had an inverse function. But without doing that, it is not invertible. And on the next slide, I'll just show you what that looks like.